So, welcome everyone to the third lecture on statistical theory. Oh, maybe with microphone is better. Welcome everyone to the third lecture on statistical theory for deep learning. I brought with me a slide where I repeat or try to repeat what we did last time. We are still at the introduction to deep learning. That's something which I like. I think it will come back if I push the button here. I introduced two kinds of neural networks already in the first lecture. We have seen what deep feed-forward neural networks now. Last lecture I introduced deep convolutional neural networks. They are applied to images, and the image is described by a matrix X, which it has D1 columns and D2 rows, consisting of zeros, values between 0 and 1, and I describe the grayscale, the image on a grayscale, so the intensity of the grayscale, or the grayscale of the image. The basic idea in comparison to feed-forward neural networks is that you arrange the neurons now in planes with positions corresponding to positions in the image, and you connect only neurons which are close with respect to the positions which they are corresponding to. You use shared weights, so for different positions you use the same weights, and you use additional pooling and subsampling layers, and I have given you an example where you can describe this formally. You start on level 0 with the output O indexed by the position ij, and then an additional channel number, and for level 0 you have just one channel because it just contains the input values. And then you define these outputs of level L with some position ij and some channel S2 recursively by applying an activation function, for which you can use, for instance, the logistic, but for instance, the real activation function sigma of x is equal to the maximum of x is 0, or the logistic thrasher sigma of x is equal to 1 divided by 1 plus e to the power minus x. To a linear combination of the outputs of the previous level, and here I want to use for each position the same weights, and I do this by making kind of convolution. So I have these outputs of the previous layer, and I look at them at position I plus, so I want the output for, or the value for position ij. I look at them at position I plus t1 minus 1 and j plus t2 minus 1, and let t1 and t2 vary at values close to 0, and I choose them from Z1 to ML, and ML is the filter size, and then I have some weights which depends only on the t1, t2, but not on the ij. On the channel S1, which I use the values from level L minus 1, and the channel S2, which I want to use compute the output, plus some offset. And then you make this for capital L many layers, and then finally you make a max pooling, or one example is a max pooling, which you make for each position aj, you look at level L on all the outputs for all the channels. Channel is the index S2 running from 1 to k sub L. K sub L is the number of channels, and you make a linear combination of these values. And this you do with the same weights for each position aj, and then you make a maximum. And that's your function. One possible function for a deep convolutional neural network. Then we started with transformer networks, where I told you that we want to apply these neural networks to text data. And generally, to apply neural networks to text data, one first has to fit this text into a sequence of numbers where you convert each word into a vector. So you convert the text to a sequence of vectors, and I describe this by using a famous algorithm where you recursively extend a symbol vocabulary which you start and assign vectors to the extent. So to do it recursively by looking at all pairs of symbols which occur within the same word, and then you choose the pair which appears throughout your text most often, and then you assign this one to a new symbol and add the symbol to your vocabulary. And that you do until you have the size which you want to get, and then you assign vectors to the extended vocabulary, for instance randomly by just using some independent random variables, or you use them from some pre-training, where you have assigned such some assignment of vectors to words already. And then last time there was the question at the very last minute where I finally stopped the discussion. Why do I do this so complicated? Why do I extend this vocabulary? Why not working with the original vocabulary? Well, I looked it up into the literature, and one reason for it is that there's a trade-off between the size of the vocabulary and the text length. Of course, yes, as if I make this one, then I get many subwords, and then the text length will be shorter. And a shorter text length is somehow better, because then the neural network doesn't have to transfer information over so many different positions. That's the reason. Or that was one possible reason for it. But de facto the reason, what I think, is people just write it, and that works better. So if you do it in this way, it works better than if you do it instead with characters. People, of course, also tried with characters. You know, this lecture is about statistical theory on deep learning, and maybe you have realized I have not presented any theory up to now. So we have not started yet with the theory. This comes after next week, or in the next week, not now. At the moment I just explain all these things, and that's like how deep learning is working, or how deep learning was produced. It was just trial and error. So people tried a lot of things, and that's always something what people say about deep learning. Is this really science? Should this be taught at university if there is nothing, just trial and error behind it, basically? And I know people who will claim, okay, you should not teach it at university because it is not science. For me, it looks a little bit like the whole deep learning business, as long as you ignore the theory, is like chemistry in the Dark Ages. We just try things. But on the other hand, it's extremely successful. So you came extremely far with this method of just trying things on real data without any theory. But what we will do here is something else. We will really start with some theory about it. And you also know a little bit from my introduction, I sometimes look at the things a little bit on an abstract way, also an abstract way, where I want to see the things in, or how I understand them in theory. But you don't really see it at the moment. Okay, to apply neural networks to text data, you can convert the text to a sequence of vectors, and then you apply something like pointwise, a recurrent neural network where you apply it word-wise for each word after another, and then you send the output back to the input again, and let it run until you reach the end of the sentence, or something like this, or end of your text. And I've already explained to you the problem with this is there are long-ranging dependency between words, and with this kind of recurrent neural network, you have to remember for a very long time what you have seen already, and that makes the thing hard. And that's where the transformer, which we deal next with, came into it. Okay, first thing. Second thing is I want to show you the list of exam questions which I have promised you. and they are already on Moodle. And I already have, I think I will show them each Monday for the week before. And I have 3 questions for the first lecture and 2 questions for the second lecture. The first question, I formulate them in English and German, because in the exam you can choose whether you want to answer them in English or in German. But I explain here only the English ones. First question is, what does deep learning mean? Give 2 reasons why deep learning became so successful in applications. Second question, how is the space of feed-forward neural network with step L and with R defined? So you define it formally, formals from the lecture. And what is the motivation for its definition? So you came up with the motivation that you want to model some nerve cells and some network of nerve cells. Then third, give 2 common examples for activation functions for neural networks. That would be the redo activation function and the logistic pressure. But of course, it's a little bit open, so you could come up with something else and say it's common too. But if you are the only one who's using it, then you have a kind of problem at this point. Then 4, explain the main ideas behind the definition of convolutional neural networks for the analysis of images. That was just on the slide. And how can one define such a convolutional neural network formally? You could repeat the formulas on the slide. And then 5th question, explain the main ideas presented in the lecture behind the definition of recurrent neural networks applied to text data. What is the problem with this approach? We just talked about it. Okay. That was the next thing. Now I think I can stop this here. Don't need this anymore. And yeah, we'll stop the beamer here. Give myself a little bit more light. And I think I can unfortunately I still don't manage to move the sound from the microphone, or to get the sound from the microphone in my computer, which is a little bit stupid, but okay. That is how life goes. So let me put it here, and maybe the sound is getting a little better. Okay, and then we go on with transformers. I already told you we start with a new representation of the text, and I do this now. Starting with the new representation of the text, of the original inputs. Oh yeah, if I missed starting with the new representation. And this new representation I denote by Z0. It depends on L vectors. And each of these vectors corresponds to one of the L input subwords in the text which I want to deal with. And I denote each of these representations by Z0, 1 until Z0, L. And each of these representation has the length d model, and I have L of them, so the whole thing are real numbers in the vector space R with exponent d model times L of the original input. And my original input was my x, depending on subword x1 to xl. And with this, in this representation, I basically forget about the positions which I have here. Well, of course, you see that in the first value there's this corresponds to the first position, the second position, but later on we will just apply linear functions to each of the components, and then we don't know anymore from which position it came from. And to deal with this, we add basically, it's the usual thing is to add some kind of positional encoding to this vector of words. So maybe with some added positional encoding. And what you will do there in practice is that you use some function defined by sinus and cosinus and add some values of it, depending on the position in the vector, but I don't want to go into details here. So starting with the new representation of the original input, we compute successively new representations of this one. And we make this n times, and recursively, so we have a Z0, and then I go up, compute first a Z1, then a Z2, then a Z3 until a Z. We compute. Successively representations and note them by ZR, and they also depend on L components, so ZR1, ZRL. They are the same kind, so also vectors in R is exponent d model times L. Of the input for R equal 1 to capital N. The capital N is the number of levels that we have here, or computation levels that we use. And then something you do something with Zn, so, and then maybe you apply some feed-forward neural network to Z, the last one. Okay, that's an example. Could be an instance. I add feed-forward neural network to Zn. And ZR is the representation of my input on level R, and it depends on representations of the L components of my input on level R. And capital N is the number of pairs of attention and pointwise feed-forward layers of our transformer encoder. Here capital N is the number of attention and pointwise feed-forward layers. input layers of our transformer encoder. So what I in fact explain in a moment is the transformer encoder. And maybe I present the whole thing with a figure. And of course what I have to explain to you next is how does this attention, it's basically a multi-head attention layer, and how does this pointwise feed-forward layer works. But before I define it, I make a picture for it, or a sketch. We have somehow the input, and we make some input embedding. Then I add some positional encoding, which I have not defined or explained to you how I do this, but I could do this. It would be standard here. And this positional encoding with some kind of wave, which you add to the whole thing. And then comes your multi-head attention. Multi-head attention. And also your feed-forward neural network. And the multi-head attention is some block, which you will see how it is defined in a few moments. Also the feed-forward is a block to feed. And each time for the multi-head attention, you split it up into 3 parts, what you have until now. So you compute 3 different things. Let it enter here. Then you compute some output, but I make a residual connection, meaning that I use my previous input and add it to the output of my multi-head attention. Then I make the same thing with the feed forward, and again I have some residual connection here. And that's one block of one pair of the attention and pointwise feed forward neural network, and you repeat this 10 times. So the output of this first block goes into a second block. The output of a second block goes into a third block, and so on. And then you get basically the set end. And for this you apply for instance, a feed-forward neural network, or something else which I explained. And the original paper by Vaswani, I think it was 2016, guys from Google who used it for machine translation. They had n equal, I think it was 7, something like 7 layers, the whole thing. Next one I have to explain to you how is this. Yes, please.
Could you repeat what the input embedding is?
The input embedding, that was what we did at the very beginning, is that you had this input as a text, and you make a vectors out of it.
Ah,
That's the input embedding. And then I add some positional encoding. I add something like it where I can reconstruct the positions, but I ignore the C. Any other questions? So, given that r minus 1 for some r and 1 to n, we compute that r by applying first the multi-head attention and afterwards the pointwise feedforward neural network. Did I write this down already? No. R is the number of 1 to n. We apply first multi-head attention. What is called the multi-head attention? And then a pointwise feed-forward neural network. A neural network responding to mail. And both are with a residual connection, which means that you use the original input and add it to the output. You will see the pointwise feed-forward neural network. That's very easy because it's like a convolutional neural network which you just apply to each of these L components separately. So you have the same neural network which you apply to each of these L's components, and it's a standard neural network with one hidden label. That's easy, and the multi-head attention, that's new. And that's what I describe next. The computation of the multi-head attention depends on matrices. So what you compute, and I could add this here, but you won't see it because I don't have enough time. What you compute here are three different things. You compute queries, keys, and values, and mix them together. And the queries, keys, and values are just matrices applied to the previous thing, so it's just linear matrix. And you apply them separately to each of the components. So you need matrices which have D-model rows each time. So the computation of the multi-head attention depends on matrices. And these matrices are de facto like the weights, the parameters of our fault transformer networks. And we have some matrix, all I call W for weights. And then the first one are the query matrix, then there are key matrix, and then there are the value matrix. They depend on the level where the level is R. And then I depend many of them. So it's a multi-head attention. I have many number of heads, and the index for the number of heads is S. And later on, it will be, or we use the letter H for the number of these heads. So that's one matrix. I also have the same thing for keys. Same indices, RS. I told you I need D models many rows. Depends what dimension here is. Forget about it at the moment. D model. And then we have something for the values. Same indices R and S. Also D model many rows. And the number of columns. In the first one, it will be, well, it's the same query and key, and I just name it after key. So it's D E, and here it's a different dimension, it's D value, which I denote by dV. It's a small D value. And you make this for S equal 1 to H. Now where? My small h, natural number, is the number of attention heads which we compute in parallel. Then the key is just a natural number, a parameter. That's the dimension of the queries and the keys. And my dimension of the values I use in a special way. I compute it in a special way, or choose in a special way. I choose it such that I will compute L of these values and compute L of these values. No, I compute H of these values, H times, and I put them all together, and then I will want to get, from all these values which I get, I want to get a value which has the length D model, so the V times H should be the model. that everything fits together. dV is equal to model divided by h. That is the dimension of the values. And it's assumed to be in M, I can remember. Okay, now I can define what we really do. So I use these matrices to compute queries. And it's the query which I compute with my data from level r-1. I compute it in the attention head number S, so S runs from 1 to H, and I compute it corresponding to one of the L positions by just using this matrix with the corresponding indices, so W query. But only the matrix with index R and attention head S, and I apply it to my representation of the ith part of the input at level r-1. And the ith part of the input at level r-1 is the ith component herein with r replaced by r-1. So I have to replace it with set r-1 minus 1 I, and I runs from 1 to L, and S runs from S1 runs from 1 to H. These are the queries. Then, in the same way, I compute the keys. Just using the key matrix, W key. S times Z r-1 I. And the values, same formula here. It's a small b, r-1 is r, value, s, z, r-1 At the moment it's just linear transformation of my input. If I do it just in this way, it's not very powerful. Yeah? It will just be linear combinations. So I need to put in some nonlinearity, and what I do is a nonlinearity. Well, you can consider as the query is you ask the question to the text. Basically, with the queries and the keys, you ask the question to the text, and Or maybe with the query you ask the question, with the key you give the answers, and then you look which one is the most similar one, and the most similar one is the you use the scalar product between the two values. So A is the representation of the ith part of our input at level r minus 1. Set r minus 1 j is the 2r minus 1 as I, and k r minus 1 as j. That's where the maximal attention comes from. In the index where the attention is maximal. Yeah. Attention is maximal. And then I use this index and use the value of this index together with the maximal attention, which I get. I multiply them both. So the one is a scalar number, the other one is a vector, and that's my new representation of part, or part of my new representation of part 5. So the value corresponding to this index is multiplied with the maximal attention. Multiplied with the maximal attention. I think I have here somewhere. Colors. And that's also nice. And now we don't use the ith value because I want to use the value corresponding to this jet hat. And r minus s I, and I multiply it with the corresponding maximal attention, which is q r minus 1 s I, and the corresponding key values p r minus 1 s, no, not j, but my index for the attention is maximal. And this we have for s equal 1 to h. And now you see, well, the maximal attention, that's a natural number, that's a real number. This one is a vector. If you look at the vector dimension, this vector dimension of the values was dimension dv. I have h, because x runs from 1 to h, I have h many of them. I put them all together, then I get a vector of the length h times dv, and h times dv was just the model. H times dv is the model. So I said epsilon r I bar. These are all of them, put them all together. Epsilon bar r1I until epsilon bar hi. And that's now the vector in our model. And then I use my residual connection to compute my new representation. And that's my epsilon bar, or my, no, it's epsilon, it's my epsilon r. I just use the old one, that was zr minus 1, and add the vectors of all these epsilon bar 1 until r1 until epsilon bar r. And that's in R with exponent d models times L, which was the same dimension as my zr minus 1. Okay, that was the multi-head attention. Now you can think about what do you have to think to invent such a thing. And what comes next is a feed-forward neural network, which is comparable rather easy to explain after I've cleaned some of the blackboard. And then you have the whole multi-head, you have the whole pair of multi-head attention and feed-forward neural network, and you apply this n times, and you get a new representation of your input. You apply some feed-forward neural network to it, and that's it. Questions up to that point? No questions? Then it's 10:41. I make a 5 minutes break for cleaning the blackboard, and I will continue with the lecture at 10:46. Thank you. Okay, I would like to go on. Which means that you could stop talking and I start talking. So next we need the output of the, we need to define the pointwise feed-forward neural network. And the output of the pointwise feed-forward neural networks is defined by, or depends on and again I need some matrices describing the weights, and I have a matrix W R1, which are the weights in the first layer of my neural network with one hidden layer, and just the weights in the linear combination. So they are applied separately to each component, which has length d model. So I need d model many of them, and then I need also to define how many hidden layers do I have, and this number is dimension of f by dimension feed forward with d model. Then I need some offset. What are the offsets which you add? And that's okay, I have to do it for each neuron, so I need the FF many. I need some weights for my linear combination in my second hidden layer. I know it by VR2. Again, it depends only now. It depends only on the level I am. Is the representation. You have DFF many neurons which you want to make a linear combination of it. So the second component should be DFF, and I want to go back to a representation of length D model. So it must be dimension D model times DFF. And then I need offsets. And what do I have to? Well, D1 was basically okay. Now I at each time I add an offset. So I need the model, and now I can define it. And the else component, or the ice component, and the ice component on level R I use again the residual connection, so I use the output of my multi-hypertension, which was Y, R, I. Which is just the ice component of this guy here. And then I add the output of my pointwise feed-forward neural network, which I use now a matrix notation to write it down in one thing. So you have your input. Maybe let me start over there. I make a linear combination out of it. So I multiply this one. Not a good idea. Make an offset, which is BR1. This gives you a vector. To this vector, I apply for each component, I apply my activation function. Then I get a new vector, and this vector I multiply now with my weights in the output layer, which is my matrix 2, and add my offsets, which are BR2. This guy. Where this activation function, and I use the redo activation function, is applied component-wise. And then I put them all together to get my ZR. ZR is equal to ZR1. That's it. And you do this for R equal to 1 to n, and then you apply some kind of network to the output, for instance, a feed-forward neural network. On level R to n, we apply feed-forward neural network. And that's it. So that's the basic, that's one of the basic things behind the large language model, and that's one of the things behind ChatGPT. Quickly present two modifications, but before that, any questions to the report?
Can you maybe
Excuse me?
about the computational complexity of this, like the Scala product that we have to compute for the
So the question is about the computational complexity, yes?
So for the multiple attention we need to compute this Scala.
For the multiple attention, you need to compute all these Scala products, yeah? Then you can look what dimensions are there, yeah? And then you can see the keys and the queries are in which, well, the query and the key have dimension, and head dimension, the query and the key, head dimension, W key, D key, yeah, and then it's something like D key squares, yeah. But you also have to do it. You do it for we do this for each S and each I and each J. Yeah? So you have an H times S squared times D squared, D squared, here.
So that's the most costly part, right?
Well, it depends on how large. I didn't tell you about how large this guy here is. Yeah? DFF will also come into play here. But I think that's the most costly part. Correct. And also you know that the D model is rather large here. So where does the model come? Oh yeah, here you also, the D model comes into play, yeah? Because you have to compute all these things, yeah? And the D model will be, I told you something about 30,000, so that's not cheap, yeah? But the whole deep learning is not about things which you can compute quickly, yeah? This is some things which run forever, or which you need very big computers. Question, please?
For the feed-forward neural network, why do the offsets not have to depend on I?
For the feed-forward neural network, why do the offsets not depend on I? Because it's a kind like in the convolutional neural network. It's a feed-forward neural network which you apply to each position in a sequence. The same feed neural. These are shared weights. And in principle, you can apply convolutional neural networks also to sequences. And they also apply to text data. And that's the kind of thing what you do here. More questions? And now I have to tell you, to make it a little bit more complicated, this is not what is really done. The argmax is not computed. Instead, there is the so-called softmax computed. So in practice, this maximal attention is computed using a so-called softmax. Therefore, non-negative numbers, well, now I need some kind of variable which I have not used before, but I think I have. Did I use u somewhere? Maybe not. Therefore, non-negative numbers, and I need an index which I have not used before. Well, a capital N I have used. Small n, well, that's usually the sample size. But maybe we make it in that way. You set. And the softmax and that's not the index where the maximum value is attained, but instead I give you a vector of 0 and 1s, where there should be a 1 where the maximum is attained and a 0 elsewhere. But I don't compute it exactly in this way. Instead I compute e with exponent u1 divided by the sum of all e with exponent u. Now I need an index. Maybe make it I equal 1 to n. E with exponent u2 divided by I equal 1 to n. E with exponent y and e with exponent n divided by. And that's a number obviously in 0, 1 exponent n. And if one of the j is very large and all the other ones are small, then of course in the j's components there will be something close to 1 and the other components something close to 0. But exactly 1 and 0 all the time will never happen. Yeah. For real numbers. So you compute a softmax instead of this one. And then you don't use this guy here, instead you used all the values times the corresponding attention. So you let J here run from 1 to L. You get L values and you make a scalar product with this guy. And the advantage of this is that this is a differential function, function of its arguments. So you can later on use some kind of gradient, or you can use gradients. Maybe I write it, so what we then do is, so in fact we would compute this y bar as I as when I let J run from 1 to L, I use my soft max value, and the soft max value for the J's components will be E with exponent this attention, Q R minus 1 as I times K R minus 1 as J, divided by the sum of all these Ex exponent Q R minus 1 as I, K R minus 1 as, now I cannot use J anymore, and I don't know which IJ, maybe L and N, make it N equal 1 to L, and I multiply with the value R minus 1 is J. So we use this definition. First point here. But the intention is to compute some kind of an argmax here. But we don't use an approximation. And then the second thing, what Vaswani and co-authors used at in the original paper, they want to introduce it to machine translation. And I explained to you only the transformer encoder. But what you do with this transformer encoder, you use your, say, text in German, you encode it by something, and then you apply a decoder to get it back to English. So you use an encoder-decoder structure. So for applications, machine translation, an encoder-decoder structure. Structure is used. And to explain this, I draw a picture again. And if you remember my picture about the encoder, what we had on the blackboard, yeah? Now I need a picture about an encoder-decoder, so you can see that the complexity somehow will double. Because I have 2 parts. Sorry for that. Okay. We go to the next picture. So again, we start on the bottom. We have our inputs. We have our input embedding. Which was just a word to vector conversion. I add some positional encoding. Then I have my multi-head attention. And I have my feed forward. Each time with the residual connection. So we have a residual connection here. Residual connection here. And this goes, my multi-head attention goes on one hand with the residual connection. This one goes again, the residual connection. And then it splits up here in the various keys and values. And I make this whole thing capital N times. Now I also have outputs. And if you want to get some machine translation, then you make it word by word. So after the first word, you have already knows what your output is. So this is somehow shifted from so you shift them. So the input is one word in front of the output, because you don't see the output before you see the input. And as soon as you have computed with your input some output, you use it as an output also here. You use an output embedding. Let's go in there. The output go in there. You start with a multi-head attention, but this time it's a so-called masked multi-head attention. The masked multi-head attention just ensures that you do not use part of the output which you have not seen yet, because you have seen only, you haven't seen your complete output. You haven't seen the output up onto some position, and as soon as your multi-head attention want to use values which you have not seen them, you just replace them by 0. So you also make this guy here, again with a residual connection. That's the first part. Goes into usual thing, query keys values. Now comes the next multi-head attention. And here comes the main trick. You compute this time only the query from your output. But the key and the values come from your input. So we go over there. Here, compute 2 more. And then we make another feed forward. And that's where my whiteboard ends. But you can imagine what is coming. Of course, again, I have a residual connection here. And I have again a residual connection here. And that's my decoder. Also in time. And honestly, I have no idea, but I think was not really described in Vaswani. You use here the output after n multi-head attention, and then you use them, the same output goes into each of these guys. But I'm not sure about that. Honestly. And you see it's even more complicated. Okay, as I told you, not the level of this lecture at the moment, and I think it was the last time that I teach on that level. I think from now on it will be clearer because we are doing more theory about this. Any questions? Okay, what did I not tell you? What this was one big achievement in natural language processing, paper by Vaswani, guys from Google, 2016. The next one was the BERT paper. I've forgotten what the abbreviation. BERT stands for, so T for transformer, B for bidirectional, and then there was an E and an R. Sorry, guys. And also from guys from Google, and they come up with a new paradigm, and the new paradigm is pre-train. So the question is, how do you get this data from your problem? And if you want to make some kind of prediction problem, then you usually need some examples where you get the text and what you want to predict, and this is very expensive to get these examples. It's not easy to get these examples. what I used for pre-training was a kind, they used some unlabeled text. So just text they found somewhere in the internet, say pages from Wikipedia, or some pages from newspaper, or some other text, or text which they can get. And they make, they produce from this text for prediction programs. One is a masked learning. You just choose randomly, say 20% of the words, and delete them. And let the computer predict the missing words in your text. And then you can give him examples of the sentence with some word deleted and the deleted word. And he can learn from that, his ways. And also, the next sentence prediction, that's something you give him from the text, you give him two different sentences, and the computer has to predict whether the second sentence is following the first sentence directly as the next sentence, yes or no. And you make it such that maybe 50% of the pairs which you present the computer, the next sentence is really the next sentence, and the other 50% not. And for both tasks, to learn weights, you learn your transformer instruction computer, and you connect this huge amount of text. You run it on a huge computer. You learn all these weights, and then you have some pre-trained model, and then you use the weights for this model, and you just say you use, for instance, the encoder, and you just add some new neural network at the very top. You keep all the weights here, and you learn the weights of this new neural network with a few labeled examples. And that was very successful. So you construct the data artificially. Okay, questions? Then we had one lecture about transformers, and well, my last lectures were both too long, so today I can stop 1 minute earlier. Thank you very much.